Hi everyone, welcome to Module 4 for Kinese 7103, which is taught in Health Kinesiology and Recreation here at the University of Utah. Today we're going to be talking about statistical inferences about parameters and how we can use our proportional reduction in error in order to make probabilistic decisions about the likelihood of observing an event. And in this case, an event might be something like the mean of a sample. And then trying to make decisions about, is this a sample that arose purely due to sampling variability? Or is it unlikely that sampling variability alone explains the effect that we observe? So, as we discussed in some previous lectures, we build a model in which we have certain parameters. And we're using the data from the sample to make estimates about what the true values of those parameters are in the population. And, as we've discussed, the sum of squared errors is an excellent method for measuring the total amount of error that we have. And this is true for reasons of efficiency, mathematical practicality, of using squares versus absolute values, and also just sort of traditionally, we find that most people have done it this way, right? So we might want to continue making decisions using this as our method of estimation. So this also means, and we have shown, that the sample mean is an unbiased, but not necessarily accurate estimate of the population mean. Right? If we're using the sum of squared errors as our estimator, the sample mean is our estimate, and we've shown that this estimate is not necessarily accurate, right? Particularly in small samples, the sample mean can bounce around a lot relative to what the true population mean is, but it's unbiased, so it's going to be kind of positive and negative in equal measure. And it's also efficient and consistent, so it has all the desirable properties of an estimator that we would want. And armed with this knowledge, we can use the tools that we already have to answer some rather important questions. So we can pitch this in a lot of different ways, and rather than looking at it as just straight numbers, I'm going to concoct an example in which we're going to test a hypothesis. Okay, so we have a hypothesis maybe that having the flu increases your body temperature. And I've formulated this hypothesis based on anecdotal observations that when I touch the foreheads of sick people, they seem warmer than me. So I've generated the hypothesis that having the flu increases your body temperature. Now, I randomly sample 10 people with the flu, and I take their surface temperature on the forehead, which is arguably not the best measure of body temperature, but it's at least a non-invasive measure that we can do affordably, and it has relatively good consistency. So let's say that over here, I have my 10 body temperatures from my flu sample, right? So these are all people who had the symptoms of the flu, and I took their temperatures. Now, the average human body temperature is about 37 degrees Celsius. So I could look at 37 degrees Celsius as my estimate, right, and see how errorful that is. How well does 37 degrees Celsius actually explain the data that I have in my sample? And if we use 37 degrees Celsius, we can calculate a deviate for each observation, right? So this person was 0.57 degrees above that. This person was 0.79 degrees above that. This person was 0.26 degrees below that. And I will have a lot of deviations or errors relative to my estimate. If I want to calculate the sum of squared errors, right, then I need to take each of these errors, square them, and then I would add them all together. And if you do that, you get 7.197. So I am off by, or the total sum of squared errors in this is 7.197. Now, what if we fit our beta with the sample mean rather than using the population mean of 37 degrees Celsius? Well, the mean temperature in this sample is 37.659 degrees Celsius. So that might not seem like a lot, but keep in mind that the variability in body temperature is relatively small, at least in our sample. And therefore, this 0.659 degree difference might actually be reasonably large relative to the variability that we observe. So anyway, our sample mean, slightly higher than what we think the true population mean is, but we can calculate a sum of squared errors around this sample mean. So again, we can take each observation, we can subtract off the sample mean, right, and we can see what we're left with. And we have, this person was, slightly below, this person was slightly above, this person was below, this person was below, this person was above. And again, I'm going to get a bunch of signed errors, right? Signed deviations relative to the sample mean. If I want to calculate the sum of squared errors, I square all of these deviations, and then I add them together, And if I do that, I get 2.854. Next, if we actually want to compare these two possible explanations of our data, as we've discussed, we want to calculate the proportional reduction in error, because the proportional reduction in error has the advantage of sort of normalizing the amount of total error that we observe. We see how much error we kind of had to work with in the beginning and how much error we've reduced it down to now. So we can calculate pre as the sum of squared errors in the compact model minus the sum of squared errors in the augmented model divided by the sum of squared errors in the compact model. Right? So again, our compact model is the simpler model, which in this case had a single value and it was an unfitted parameter. So we didn't fit this from our data. We just said 37 is the value. Here we're estimating, right, a parameter in the population. So this is technically a more complicated model, and this is our SSEA. So when we take that, we're going to do 7.197 minus 2.584 divided by 7.197 in order to get a value of pre. Plugging those values into the equation, you can see that we get 0.603. So there's approximately a 60% reduction in the sum of squared errors by using the sample mean rather than using the known population mean of 37. So this seems pretty good. We've significantly reduced the amount of error in our sample by using our sample mean. Now, does this mean that having the flu increases your temperature, however? Right? That's the big question. And at the moment, we don't know that that's true. And in fact, actually, that causal inference is going to be hard for us to make from this sample because we didn't randomly assign people to having the flu or not. But just on the basis of the data alone, we can't say that is it unusual for people with the flu to have higher temperatures, right? So sort of causal arguments are a separate issue around design and the method of analysis. But in this situation, we're just trying to say, do we think that people with the flu have higher temperatures? Anyway, that's a bit of a tangent. How much better does an explanation need to be before we decide it is the better explanation? That's what we're really after. This 60% reduction in error certainly seems pretty good, but how much better does it need to be before we think, okay, this isn't just a random fluctuation. We don't think we just happened to get a sample with a high sample mean. We think there might really be something else going on here. So this is when we ask this question. How can we use the proportional reduction in error to actually make an inference from our sample to the population, right? So now we're going to generalize from our sample to the population of people with the flu, and we're going to need to try to make a decision about what the average body temperature for someone with the flu actually is, and is it the same or different from the average human body temperature of 37 degrees Celsius. So recall that the sample mean is always going to produce the smallest sum of squared errors for a set of numbers. Thus, it's not unusual that SSEA was less than SSEC in this situation. Indeed, the only time they'd be the same, right, would be if our sample mean happened to be 37 degrees Celsius. If it was exactly 37 degrees Celsius, then SSEA and SSEC would be equal. In all other cases, the sample mean is going to be a better approximation of the data than the population mean, right? And therefore, SSEA is going to be smaller than SSEC, right? So this is relates to the same reason as why we had to divide the standard deviation by n-1 rather than n. The sum of squared errors estimated by a sample mean is always going to be closer to that sample mean than the population mean, which constricts the sum of squared errors in your augmented model. Thus, it's not surprising that SSEA was smaller than SSEC. And in order to make an inference, we need to decide, was SSEA sufficiently smaller than SSEC in order to make the result statistically interesting? In sort of common parlance, people might talk about this as being statistically significant, but there's a lot of debate around the use of the word significance. And I think it's more appropriate to talk about this result as statistically interesting. Okay, so do we think that this is something that arose through sampling variability alone, or do we think it is unlikely that sampling variability alone explains these data? So is the reduction in SSE large enough that we think it is unlikely to have happened by sampling variability alone? In class, we're going to show the sampling distribution of pre using simulations, right? So we'll look at how much do we really expect pre to change from one sample to the next. But for now, we want to focus on two key concepts. First, right, the proportional reduction in error is always going to be greater than or equal to 0 in this situation because the sample mean will always provide the smallest SSE for a set of numbers. Okay, so it's not surprising that it's a smaller sum of squared errors. So the question is, how much smaller does it need to be? Now, the larger the proportional reduction in error, the less likely we think the result is to have occurred by sampling variability alone. Right? Let's say if our sampling mean was 40 degrees Celsius, right? That seems very unlikely to have arisen by chance. And actually, those people would be in a real bad fever state. They should go to the hospital. But if our sample mean was that different from the population mean, just intuitively, right? You probably think that there's something else going on there. That's not a random fluctuation. And now we don't want to reason just from intuition, but that intuition is correct. And the larger the difference, right, the larger the disparity, the worse of an explanation 37 degrees is, the more that suggests that there's something else going on. Now, that doesn't mean it can't happen, right? Very, very strange events and very unlikely events happen all the time. But it would have a very low probability of happening due to sampling variability alone. Thus, if the variability explained by an estimate is large compared to the residual variability, this suggests that there might be something systematic rather than random happening in our data. So we're going to elaborate on this in more detail, and once again it comes down to my preferred expression of knowing thy distributions. Right? So for us to make an inferential statement about the probability of observing a proportional reduction in error, we need to make an estimate about the variance in the population. And how much is that sample mean going to change from one sample to the next? And if we expect relatively little variability from sample to sample, a big change is unlikely. If we expect a lot of variability from sample to sample, a big change maybe isn't that unlikely, right? And as we've shown, the sample variance is one tool we can use to estimate the population variance, right? And just as a reminder, in the population, we would write the variance as sigma squared, but we don't know what sigma squared is, so we need to estimate it using the sample variance, right, which is written as S squared, which is calculated as the sum of squared errors divided by n minus 1. And when we divide by n minus 1, this gives us an unbiased estimate of what the population variance is. So it might not be perfectly accurate, but we can at least say, okay, in any given sample, the sample variance is going to be an unbiased estimate of the population variance, and therefore we can use that sample variance to make an estimate about variability in the population, and we can use that estimate to make a decision about how large a proportional reduction in error we find statistically interesting. So we're going to go through this in more detail, but critically the shape of the sampling distribution for pre depends on the number of estimated parameters in the model and the number of observations in the sample. So when we think about the sampling distribution, we're not going to have just one sampling distribution for pre. In fact, we're going to have lots of different potential sampling distributions depending on how much data we have in the sample and how many parameters we're estimating. When we're estimating one parameter, right, in this case we're estimating the mean, and we have 10 observations, we have a very particular sampling distribution. And we can simulate this, and we can, in lab, we'll walk through the math as well to show that, okay, when we have a sampling distribution with 1 and 10 degrees of freedom, what proportional reductions in error are expected and which ones are unusual. As the number of observation increases, we know that S squared is going to be a more consistent approximation of sigma squared, and thus a larger pre is going to be more surprising. As the number of parameters increases, we generally expect to explain more error, even just by chance, and thus a larger pre is less surprising. So these two parameters, right, the number of parameters in the model and the number of observations in the sample, somewhat work against each other, right? And so if we have a large data set with a single parameter and explains a lot of the variance, that's pretty compelling, right? But if we have 10 parameters that we're estimating and they explain the same amount of variance, well, now that's less compelling because we put 10 parameters in there and we expect all of them to explain some variability just by chance. So again, the number of parameters in model A and the number of observations in the sample work against each other in how we interpret the pre we observe. And we need to take both of those things into account when we calculate our sampling distribution. However, critical values of pre and its sampling distribution are actually pretty rare in statistics textbooks. And instead, it's much more common to convert the proportional reduction in error into what's known as an F value and interpret it with respect to what is known as the F distribution. It's based on the same idea, though. The F distribution tells us how much variance we expect and what change in variance we expect due to random sampling. So in the next module, we're going to talk about the F distribution in detail. We're going to show you how it changes as a function of the parameters and as a function of the amount of data in the sample. And we're going to show you how we can draw some inferential conclusions when we calculate the F data in our sample and compare it to the known F distribution. And then if that F value is quite large relative to what we would expect, we think that something statistically interesting is happening in our data.